So we will start the session now, and let's see who will join later. Is the screen visible?
Yes, ma'am.
You can see the changing of slides, right?
Yes, yes.
Okay. So, hello everyone. Today on the course of mechanics, this is the live session 4 of the course Mechanics of Fiber Reinforced Polymer Composite Structure. And today I'm going to discuss some sample problems which will be helpful for you to solve your assignment number 5. Okay. So now in this, after the uh, fifth week, we started studying about the micromechanics of the lamina. Before that, we studied about the macromechanics of the lamina, where it considered that the lamina is homogeneous. Whereas now we are going to move towards the micromechanics of the lamina. So here we consider the different components of the lamina, that is the fiber, resin, and along with that comes voids. So as the first question is to find the true statements from the given options, and here we talk about a void. So void is some empty spaces or pores that may be present inside when a composite is formed by the resin and the fibers. This depends on the different methods of manufacturing, and some manufacturing process gives less voids whereas some gives more, and these voids the are empty spaces and can also cause cracks and causes this propagation. So our main objective is always to have less amount of voids, as it can reduce the mechanical properties and the lifespan of the final composite. So here in the options you can see the first option says that the presence of voids in FRP composite leads to reduction in shear strength and stiffness, which is a correct answer, because as I said, presence of voids causes reduction in the mechanical properties of the final composite, and here it is talking about reduction in the shear strength and the stiffness of the composite. Where next statement is the opposite of the first statement, that it increases in shear strength and stiffness, which is false. Then the third statement says presence of the void in a FRP composite leads to reduction in the compressive strength and stiffness, which also signifies the mechanical properties, and because of voids there is reduction in the mechanical properties. So this is a correct statement. Whereas the fourth statement is the opposite of the third one, which will be false. That it doesn't increase in compressive strength, whereas it actually reduces the compressive strength and the stiffness of the final composite. Next question is a numerical. It says in a unidirectional glass epoxy lamina, Young's modulus and Poisson ratio of the glass fiber and the epoxy is given, and also the fiber volume fraction is given. So we have to find the longitudinal Young's modulus of the lamina. Here, as taught in the class, we are considering a lamina, as you can see in this diagram, and we are putting a load along the direction 1. So when there is a load in direction 1 of the whole composite, the composite contains the matrix as well as the matrix in this color, and the gray one is fiber here. So when you will put load in direction 1, there will load in both the fiber and the matrix, which will sum up to be the total load on the total force on the whole composite. So here you can see by putting this equation, the force on the composite will be the sum of that in the fiber as well as the matrix. Now force is equal to the stress into the area of the area. So putting that values of the composite fiber and matrix, we get this equation. Now from Hooke's law, stress is equal to strain into the Young's modulus. We put the value here. Here we take this assumption that there is a perfect bonding between the matrix and the fiber, because of which when there is load in one direction, there will be in one direction, then there will be equal deformation of the matrix as well as the fiber. Because of that, we can say that the strain of the total composite will be the same that the strain get for the fiber and the strain of the matrix. By taking this assumption and removing the strain term from this equation, we can get the final equation of Young's modulus in terms of the Young's modulus of the fiber, the volume fraction, fiber volume fraction, and the Young's modulus of the matrix. Here you can see AF by AC is given, the area of the fiber and area of composite, which is also equal to the fiber volume fraction, and AM by AC is the matrix volume fraction, which is 1 minus fiber volume fraction from this equation when we consider the fiber in terms of a rectangle and we solve it. So this is the final equation you will get to find the longitudinal Young's modulus. Putting the values, you can get this answer. Next question, with the same data they are asking, what will be the transverse Young's modulus of the lamina? Now here, as they are talking about transverse, the load is along the direction 2, which is not the axis of which the fiber is aligned, but it is in the transverse of the fiber alignment axis, that is in 2. Now here, the total deformation of the composite will be equal to the sum of the deformation of the fiber and the matrix. Putting the value of strain, the deformation is equal to strain and the thickness. We get this equation. Now from Hooke's law, strain is equal to the stress divided by modulus. We get this equation. Here we are assuming that the stress will be of the whole composite will be equal to the stress of the fiber and the matrix, because when we are putting the load along the two direction, the whole how much the same amount of stress will be on the fiber also and the matrix also. They won't add up, they will be equal, and that will be equal to the whole stress, that is that whole load as stress on the whole composite. So they are all equal. Putting this assumption and removing the values from here, we get this as the final equation of the transverse Young's modulus in terms of the Young's modulus of the fiber, of the matrix, and the volume fraction of the matrix and the fiber. Put the values in the equation, we can get the solution for transverse Young's modulus. Any doubts?
In that question number 1 and 2, the Poisson's ratio is just a dummy data, right?
Where?
To question number 2 and 3.
We are coming to more questions. So there you will use Poisson. It is like one data is given for 3 questions. So question number 2 and 3, it doesn't use Poisson. Next here you will get the use of Poisson ratio. So that's
Okay.
so question number 4, with the same data, we are asking the Poisson ratio of the lamina. To find the Poisson ratio of the lamina, here we assume that the load is along the direction 1. So, as said in last to last question, because of the perfect bonding, the strain will be same for the composite fiber and the matrix in the longitudinal direction. As Poisson ratio is the ratio of the transverse by ratio of the transverse load divided by the longitudinal load. Here we are considering that in the longitudinal direction the strain is equal for the whole composite fiber and matrix, but in the transverse direction the deformation will add up. So here you can see the deformation of the composite in transverse direction is equal to the deformation of fiber in transverse direction and the deformation of matrix in transverse direction when the load is along the direction 1. Now from this equation, deformation is equal to the strain in the transverse direction and thickness, and we can say we know the Poisson ratio is minus of the strain in transverse direction divided by the strain in longitudinal direction. We will put these values in the equation, and here the in longitudinal direction all the strain values are similar. So finally for Poisson ratio we will get this equation in terms of the Poisson ratio of the fiber, the matrix, and the volume fraction of the fiber and matrix. So as the question asked to find the Poisson ratio of the lamina, we put the values from the data given in the equation and we can get that of the lamina. Now question number 5, for the same data they are asking what will the value of Q11 in the reduced stiffness matrix Q. As we have already studied the reduced stiffness matrix, here Q11 in terms of known parameters which can be found from mechanical testing, that is the modulus, the Poisson ratio, and shear modulus. So in their terms we can find the value of Q, the reduced stiffness matrix value. So they asked Q11. From this diagram you can see the value of Q11 can be found by E1 by 1 minus mu12 mu21. So we will put values here and we will find the value of the Q11. And also from the last question you found Poisson ratio mu1 2, and there is a relation between mu1 2, mu21, E1 and E2. From that you can get mu21 and put the value here. The next question is, the fibers are arranged in a square array in a unidirectional glass epoxy lamina having a volume fraction of 58%. The in-plane shear moduli and Poisson ratio of the circular glass fibers are given, and also of the epoxy is given. Now we have to use the Helfin-Tsai equation and find the in-plane shear modulus of the lamina. So we know Helfin-Tsai modulus. Helfin-Tsai equation is used because for transverse properties, the mechanics of material approach was not giving us accurate answers, accurate solutions. For that's why for transverse properties only we are using the Helfin-Tsai equation. So sir has taught this is the equation where m is the modulus and zeta is a reinforcement factor, which for in-plane shear modulus evaluation we consider equal to 1, and then we have given the equation of eta in terms of the modulus of fiber and matrix and zeta. So we have to take care of this point that zeta value will be 1 for in-plane shear modulus evaluation. Okay, and for transverse modulus it is equal to 2. So as this question they asked to find for in-plane shear modulus, zeta we will consider as 1. So now we put the values in the equation. Eta we will get, we are given the Young's modulus. No, here we are given the in-plane shear modulus of the fiber and matrix, and the zeta value will be equal to 1. We will get eta. Then put the value of eta and zeta and volume fraction, which is given 58% in this equation. We will get the ratio of in-plane shear modulus of the lamina divided by that of the matrix, and it is already given here gm equal to 1.2, and we can get the final value of in-plane shear modulus of the total lamina. Now the next question is, circular cross-section fibers are arranged in a square array in a unidirectional glass epoxy lamina having a volume fraction of 65%. The Young's modulus and Poisson ratio of the circular glass fibers are given, and that also epoxy is given. If E2 mm is the transverse Young's modulus evaluated using mechanics of material approach, and E2 HP is the transverse Young's modulus evaluated using the Helfin-Tsai model, then we have to find the ratio between them. So as we know, the mechanics of material approach was initially we found was derived, but the transverse properties were not giving accurate answers from the compared to the experimental results. That's why Helfin-Tsai model was introduced, which was a empirical semi-empirical model, which was giving approximately the same values as that of experimental. So when we take the mechanics of material approach, the value we can find the value of the transverse Young modulus at inverse of the volume fraction of the matrix divided by the Young's modulus of the matrix plus the volume fraction of the fiber divided by the Young's modulus of the fiber, and we will find the inverse, and we can get the transverse Young's modulus according to the mechanics of material approach. Then we go for the Helfin-Tsai model. Here, as I said, for transverse modulus evaluation, we have to take the value of zeta equal to 2, and as shown in this previous question, the equations which we have to follow, we can find the value of eta from the given data, and putting the value of eta and zeta and volume fraction in this, we can get the value of the transverse Young's modulus for the Helfin-Tsai model, and then we have to take the ratio of these two datas, and then we will get the final answer. So next question is, in a unidirectional glass epoxy lamina, Young's moduli and Poisson ratio of the fiber and matrix are given, and also of the epoxy is given. So the ultimate strength of the fiber and matrix is also provided. So we have to find the critical volume fraction. Now critical volume fraction is when in any composite, when it is formed of a matrix and the fiber, and we consider the failure of the composite is when the fiber breaks. Okay, but there is a certain number of fibers that is required to be put in the matrix, then only its strength will be useful, and that is called as the critical volume fraction. The critical volume fraction is the minimum number of fibers that should be added in the matrix such that the whole composite's tensile stress will be, the ultimate stress will be more than that of the only matrix ultimate strength. So as taught by the sir, this equation, the equation was derived for this condition, and from that we got the equation of the critical volume fraction. So all the data is available in the question. When we put the value, we can get the critical volume fraction in this case. And the next question is, what will the minimum volume fraction? So for minimum volume fraction, the condition is that the ultimate tensile stress should be greater than the product of the volume fraction of the matrix and the ultimate tensile stress of the matrix. So when we derive for this condition, we get the final equation of V minimum volume fraction, and by putting the values given in the question, we can get the value of the minimum volume fraction. So next question is, in order to ensure that the addition of fiber to the matrix leads to tensile strength of the composite more than that of the matrix, what will be the condition? As I said here in this question, that the critical volume fraction is the minimum volume fraction, that means the minimum number of fibers that should be added in the matrix such that its ultimate tensile strength is more than only the matrix. So taking this condition in mind, we can say that the actual answer should be when the fiber volume fraction is more than the critical volume fraction. Only then the only when the volume fraction is more than the critical, then the addition of more fibers you are adding, then the tensile strength of the composite will be more than only the matrix. Any doubts? Yeah.
I mean that question number 8 and 9.
This one?
8, 8.
Huh.
Here, this first one, sigma mu, that is,
Ultimate stress of the matrix.
we have to enter it in pascals only, or can we enter it in megapascal?
We can enter it megapascal. The units will cancel in the equation.
Then, if we come to Young's modulus,
Huh? It's in
there
gigapascal.
also we, so if we follow uniformly that stress and Young's modulus,
They
if
should
we
have
take both
same
as
unit.
um,
Here, or you can take it in Pascal. Here, when I solved, here we took it in Pascal only. There you can see e to the power 6 is 10 to the power 6. So we took all the values in Pascal and then we solved.
in the final answer we get, it is automatically in percentage.
It will be fraction that you can convert into percentage.
No, now it is 0.391 percentage, because in assignment we have to enter the value. So actually in the previous problem which we solved, now in this class only we solved problems by taking volume fraction. So there, I think question number.
Fraction only.
Okay, so we need not have to convert it into percent.
Okay, hello, Vishwas.
Yes, ma'am.
I just solved this. Okay, you will get this value in fraction, then you have to multiply it with 100 and give percentage. Because when I solved it, I got it as 0.003736.
Yes, ma'am.
Okay. So
So
we'll
now,
change
now
it to
in the
percentage.
assignments, in the assignment now, I think in assignment 5, there are two questions of same kind. Now in the question they have asked as a fraction, volume fraction, and options are not given like this. They have asked us to enter the answers. We have to enter. So we have to enter that 0.0 value, or we have to enter by multiplying 100.
By multiplying 100 you enter.
Okay.
Because in all the questions also, whenever they talked about fraction, they did in percentage. So by
Yes, yes.
multiplying in 100, you write the answer. Okay.
Okay, okay.
Oh. Anything else? Any other doubts? Okay, then we will end this meeting, this session. We will
Okay.
discuss the next session. In next session, we will discuss the next assignment, that is example question of that. Okay, then
Okay.
thank you for coming.